Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In this title Numerical Analysis, in this episode we are going to talk about floating point representation. In the previous session we were talking about error propagation that may occur during numerical computations. Various types of error were discussed and the drawbacks while the binary number being converted to decimal number by the computer were discussed. So, in this session we are going to talk about the errors estimation, computational methods for error estimation and the floating point representation of an arithmetic number. The previous session we discussed how a number fed in the computer is being converted to binary number by the computer, and before the printout is taken by the person using the computer, it is again converted to decimal and the computer gives you the ultimate decimal number. So, that kind of representation had some drawbacks. So, in this episode we are going to talk about floating point representation of an arithmetic number so that errors may be decreased. So, floating point representation. Basically, there are two types of arithmetic operations. The two types of arithmetic operations are carried out in computers. One is integer arithmetic, another one is floating point arithmetic. Basically, integer arithmetic deals with the integer operands that are numbers without fractional parts. That is, it consists of only whole numbers type. So, it is mainly used in counting like 1, 2, 3, 4 like that. It is used in counting and also as bases, that is as subscripts. That is, when the set X has n elements, how will you represent the n elements using the subscripts as x1, x2, x3, etc. up to xn. X suffix 1, that 1 represents an integer. So, that suffix or subscript 1 is used as integers. However, most scientific and engineering calculations are carried out in floating point arithmetic. What is actually floating point arithmetic? It uses numbers with fractional parts, whereas integer arithmetic uses numbers without fractional parts. So, floating point uses the numbers with fractional parts as operands and it is used in most computations. Basically, because of economic considerations, computers are so designed such that each location, that is also called a word, in memory stores only a finite number of digits. This is based on the capacity of the computer storage. So, one method of representing real numbers in computers would be able to assume a fixed position for the decimal point and stores all numbers after appropriate shifting if necessary with assumed decimal point. Such type of convention is used. The maximum and minimum in magnitude numbers that may be stored in computer having memory in which each location can store only 6 digits with a provision to store one or more signs are 9999.99. This is 6 digit type of number that may be stored in the computer. That is a maximum magnitude number, and the minimum magnitude number is 0000.01 respectively. So, this range was quite inadequate in practice because we cannot always stick on to the 6 digits, or this particular two numbers cannot be the maximum and minimum always. Hence, a different type of convention for representing real number is adopted. This convention aims to preserve the maximum number of significant digits in a real number, significant digits in the sense more number of digits in a real number, and also increases the range of values of real numbers stored. So, this representation is called normalized floating point mode of representing and storing real numbers. Mantissa and exponent. For example, take a decimal number being represented, an n digit floating point number in base b can be represented as a is equal to plus or minus 0 point d1, d2 etc. up to dn base b, b power e. Base b, this can be, if it is b is equal to 2, then we get a binary representation of the number, where point d1, d2 etc. up to dn suffix b is called mantissa. This particular part is called mantissa and e is the exponent. For example, consider the binary number as 0.101, 101, 101 into 2 power 11. Okay. How this is represented? 0.101, 101, 01 e 0101 e. Okay. Here this particular part 0.101, 10101 is called the mantissa, and this particular point 1011 is called the exponent. The precision of the floating point numbers on any computer is determined by the number of digits used in the mantissa, which in general varies. Computers having 48 bits to represent a single precision number, real number, single precision real number. For example, these 48 bits are allotted as follows, that is, in general allocate 1 bit for sine, 7 bits for the exponent, that is after the mantissa, and 40 bits for mantissa. Okay. Thus, the range is limited from 2.939 e minus 39 to 1.701 e plus 38. The numerical precision in this case is 11 decimal digits. Okay. Similarly, for 48 bits we have been talking, and similarly if the computer is having 32 bits to represent a single precision real number, the following are the allocations for sine, exponent and mantissa. That is, allocate 1 bit for sine. 1 bit is enough because either plus or minus will come, and 7 bits for exponent and 24 bits for mantissa. In this case, the limit ranges from 2.939 e minus 39 to 1.701 e plus 38. So, the numerical precision in this case is only 6 decimal digits. When 64 double precision arithmetic is used, this double precision and single precision will be discussed later. The computer output may be accurate even up to 16 decimal digits. Again, consider the floating point representation. To be more elaborate, let us discuss this. That is, let beta denote the number base. There we have used b, here beta is used, being used in the computer. Then a non-zero number x in the computer is stored essentially in the form of x is equal to, this is in general, sigma 0 point as discussed a1, a2 etc. up to at, suffix beta, beta power e. Just compare with the previous one, the same thing. Here a is equal to plus or minus point d1. This plus or minus is now generally represented as sigma, and this is having some other representation as a point a1, a2 etc. up to an, and instead of a b we are taking beta and beta power e. Okay. With sigma is equal to plus 1 or minus 1, so, and this particular t digits, isn't it, 0 less than or equal to ai less than or equal to beta minus 1, and e is always an integer, this particular part, and we have a point a1, a2 etc. up to at, suffix beta is actually a1 by beta power 1 plus a2 by beta square plus a3 by beta cube plus etc. plus at by beta power t. Okay. The term sigma is called the sine and e is called the exponent, and point a1, a2 etc. up to at is called the mantissa of the floating point x. So, this is how any decimal point is represented in the floating point representation. Preceding a1 is called the radix point. preceding a1, that is whatever here particularly 0 is the radix point here, preceding a1 is the radix point. For example, the decimal point beta is equal to 10, for binary point beta is equal to 2. The integer t gives the number of base beta digits. This particular t here gives the number of base beta digits in the representation. We will always assume that at is not equal to 0, giving what is called a normalized floating point representation. So, this is how the decimal number is represented in terms of a floating point arithmetic method. We will also assume that L is less than or equal to E is less than or equal to U, which limits the possible size of x. That is, the number x is equal to 0 is always allowed and requiring a special representation. Now, after a number is being represented as a floating point in the floating point representation, then the computer has to do the operations. What type of operations it may do? It will do the operations like addition, subtraction, multiplication, division, etc. So, we have to talk about floating point operation also. Let FL of x denote a floating point number, that is a decimal number being represented in the form of floating point representation in terms of sigma, mantissa and exponent. So, a real number x can be translated into an n beta digit floating point number FL of x in two ways, that is rounding and chopping. What is meant by rounding? In this method, rounding, FL of x is chosen as the normalized floating point number nearest x, where symmetric rounding to an even digit is used in case of a tie. What is meant by chopping? Chopping in the sense cutting off. In this, FL of x, that is floating point representation of x, is chosen as the nearest normalized floating point number between x and 0. For example, consider the floating point representation of 2 by 3. Actually 2 by 3 when you do numerically it is 0.6666, it goes on up to infinity and it is not a convergent number. Okay. So, what you will do if you want to round off, you round it off at the second decimal place itself, 0.67 into 10 to the power 0 rounded off. And if you want to chop it off in the sense cut it off, because it is going on up to infinity, if you want to cut it off, just take only 0.66 into 10 power 0 chopped. Okay, this is a decimal number, this is actually a fractional number, isn't it? Fractional number, decimal number, and this is a whole number. Just consider a whole number, floating point representation of minus 838. 838 is rounded off as 838 to be represented in terms of a floating point representation in the sense plus or minus, like so minus is the sign here and it should be represented in the form of a 0 point, because 0 point a1, a2 etc. up to an is considered. So, it is actually minus 0.838 into 10 to the power 3. Okay. When you round, this is the actual number. When you want to round it off, it is taken as minus 0.84 into 10 cube. So, here minus is the sigma sign and 0.84 is the mantissa and 10 power cube is the exponent part. Okay. And if you want to chop it off, the last digit should be taken out. So, minus 0.83 10 cube is the chopped number. Next, we have to talk about what is meant by overflow and underflow. When the exponent bounds are violated, then the associated number x, what is the exponent bounds we have taken? That is capital L is less than or equal to E less than or equal to U. So, when the exponent bounds L is less than or equal to E less than or equal to U are violated, then the associated number x represented in the form of x is equal to sigma point a1, a2 etc. up to at suffix beta power e. Okay. the associated number x being represented as sigma point a1, a2 etc. up to at suffix beta, beta to the power e cannot be represented in the computer. Okay. We now look at what this says about the possible range of the magnitude of x. So, first of all, xl is 0.1000 etc. 0 suffix beta, beta power l. Okay. This is actually beta to the power l minus 1. This is the smallest positive floating point number, smallest positive floating point number. Using gamma is equal to beta minus 1, okay, the largest positive floating point number is xu is equal to point gamma, gamma etc. up to gamma suffix beta, beta to the power u, and this is 1 minus beta to the power minus t into beta to the power u. Thus, all floating point number x must satisfy xl less than or equal to modulus of x less than or equal to xu, where xl is the smallest positive floating point number and xu is the largest floating point number. Okay. Within the Fortran language of most computers, if an arithmetic operation leads to a result x for which modulus of x is greater than xu, that is if it goes beyond the bound xu, then this will be a fatal error and the program will terminate. When an error occurs, the program will terminate. This error is called overflow error. In contrast, if you have 0 less than x, modulus of x less than xl, okay, again it is violating xl is less than or equal to mod x, then usually FL of x will be set to 0 and the computation will continue, and this is called underflow error. Consider this example. Consider evaluating x is equal to s to the power 10 on an IBM mainframe computer. There will be an underflow error if s to the power 10 is less than 16 to the power minus 65. Mainframe computer uses 16 digits, 16 bits, therefore 16 to the power minus 65. Thus, you will have x is equal to s to the power 10 will be set to 0, if mod s is less than 1.49 into 10 to the power minus 8. Also, there will be an overflow error. Underflow error happens when s is less than 1.49 into 10 to the power minus 8, and overflow error occurs if s to the power 10 is greater than 16 to the power 63. Okay. Or equivalently we can say mod s is greater than 3.9 into 10 to the power 7. So, this is what is overflow and underflow errors. Taking another example, if we take two decimal digit numbers x is equal to 0.20 into 10 to the power 1, it is actually 2, and y is equal to 0.7 into 10 to the power minus 6, and z is equal to 0.3 into 10 to the power 1 is equal to 3. It is actually 10 to the power minus 6. So, you have to write this as 0.0000077. Okay. Actually, here x is equal to 2 is 0.2 into 10 to the power 1 is equal to 2, and y is equal to 0.77 into 10 to the power minus 6 is written as 0.00000077. But when you want to add with x, this should be represented in the form of 10 to the power 1. So, I will put one more 0 and into 10 to the power 1. Now, you can add, and x plus y is 0.200000077 into 10 to the power 1. Again similarly, x should be written in the form of 10 to the power minus 5. How will you take 10 to the power minus 5? Just multiply it with 10 to the power minus 6 and then subtract. You get 0.154 into 10 to the power minus 5. Okay, that is it should have the common exponents so that we can add or subtract the Mantissa part. Okay. Similarly, x by z, x divided by z, x is having a 0.20 into 10 to the power 1. So, no problem, and z is a 0.30 into 10 to the power 1. So, it is actually 2 divided by 3 goes as 0.6666 into 10 to the power 1. Hence, if omega denotes one of the arithmetic operations, that is addition, subtraction, multiplication or division, then omega star represents floating point operation. Like usual multiplication, usual addition, the floating point operation is not equivalent. For example, x omega into y is x omega is usual multiplication and x omega is multiplied with y using floating point representation is not equal to the ordinary multiplication of x omega y. That is x and y are multiplied through floating point representation, floating point operation. Okay, and x and y, this is usual multiplication. Okay, that is x and y being multiplied usually is not equal to floating point multiplication. Although floating point operation omega star corresponds to omega, it may vary from machine to machine. It depends on the bits the computer uses. So, omega is usually constructed so that that operation is done in such a way that x omega into y, that is floating point multiplication of x and y, is equal to the floating point representation of the usually multiplied number x y. Thus, the floating point sum or difference or product or quotient of two floating point number usually equals the floating point number which represents the exact sum, difference, product, etc. of the two numbers. See, we take x omega star y, that is floating point multiplication of x and y is equal to floating point representation of the multiplied result of x and y. I have explained with multiplication. This can be done with multiplication or whatever the omega can be any type of operation, addition, subtraction, multiplication or division, etc. So, what does it says in words? That is floating point sum, that is addition or subtraction or product or quotient of two floating point numbers usually equals the floating point representation of the exact sum, that is exact addition, difference, product and quotient of the two numbers. Unless overflow or underflow or error occurs, that is we may have x omega star y is equal to omega x y 1 plus delta for some delta with the modulus of delta is greater than or equal to u, where u is the rounded off number. Thus, the consequence of floating point representation is that associative and distributive laws of arithmetic are not always valid. That is, you cannot shift the numbers using associativity. That is, a plus b is not equal to a minus c plus b, and similarly a into b minus c cannot be distributed as a b minus a c. Now, consider a binary number x. According to the floating point representation, it can be written as x is equal to sigma x bar into 2 power e, where sigma is actually plus or minus 1 and e is an integer, or x bar is a binary fraction satisfying a 0.1 base 2 is less than or equal to x bar less than 1. In decimal, this x bar is actually 1 by 2 is less than or equal to x bar less than 1. If x is equal to 1101.1011, sigma is plus 1 and e is 4, 4 is actually written in the binary form as 100 suffix 2 and x bar is point, e is 4 in the sense 2 power e, 2 power 4. The 4 decimal places is being shifted. So, here 0.11011011 suffix 2. In this session, we discussed about various concepts related to floating point representation of a number, that is the number may be decimal number or binary number. and also floating point operations of two numbers were discussed. Also, overflow and underflow errors, that is the maximum and minimum that a number can take, maximum values and minimum values that is allowed by the number, is also done with an example. Based on the discussion in this session, the following questions may be posed. How will you represent a number as floating point arithmetic? Brief about underflow and overflow errors. Also brief about floating point operations. Thank you.